Thanks, everybody, for sticking around after lunch. So it's kind of a weird juxtaposition, and I will readily admit that I know very little about Mars, so the first part of this talk is mostly going to be about here's what's interesting about Mars. It may not actually deal with some of the talks, but interesting information you can have. As you can see, this is a picture of the limb of Mars, so we've got both of a picture of the atmosphere involved there and then the solid surface. And craters, which we will hear a little bit more about later today. So first, I want to introduce the major players. We have the Earth and Mars. Just to give you guys a little bit of particulars, the Martian day is a little longer than the Earth day. It takes about 600 and some days to get around the sun. Those are Martian days, by the way. And it weighs, about a tenth of the mass of the Earth, and it's about half the size. So it's cold, it's dry. The surface temperature actually varies by more than a factor of 2. It goes from about 130 K at its least point to about 310 K. And the surface pressure is actually about 6 millibars, and varies from about 4 millibars to greater than 8 millibars. So that also varies by more than a factor of 2. The surface gravity is a little lower, and clearly my slide didn't show up entirely, but for example, the Earth's atmosphere is made up of principally nitrogen and oxygen and argon with a little tiny bit of water and CO2, whereas the Martian atmosphere is mostly CO2 and nitrogen and argon and a little bit of oxygen and then water vapor. And the Martian atmosphere is very, very tenuous. Just to give you a little picture of what the Earth-Moon system looks like in perspective, this is to scale. Because we're going to be talking about Mars, we should also look at the Martian moons to scale. Yeah, that's right, you should laugh. If you can't see it, this is Phobos, and this is Deimos, and those are to scale. We're taking an interesting betting pool because Phobos is actually on a degrading orbit. So sometime in the next 50 million years from now, not then, now, it will eventually, thanks, someone got the reference, it will eventually collide with the solid surface of Mars. So if you want in on the betting pool, you have to play with some pretty big names like Emperor Shaddam IV and the cyber hegemon? There's a couple different pronunciations there. So, moving on. The reason why you can't see it is because this is the size of Phobos. Here's Madison for scale. So, very tiny moon. It's most likely captured. If we start looking at the solid surface of Mars, we get some very interesting features. These are the northern plains. They are relatively crater underfull, whereas the southern portion of Mars is incredibly cratered. One of our talks will feature the Acidalia planitia. I'm sorry. Again, I'm not an expert on Mars or Martian pronunciation. But it's this plain right here that has a few impact structures that could give us some clues about some of the sedimentary structures that may underlie a lot of the surface of Mars. And so you can see this dichotomy where you have a fairly flat northern hemisphere and a very well cratered southern hemisphere. And that dichotomy between the low-lying northern hemisphere and the uplifted or high altitude southern hemisphere is very interesting. I don't think there's been a very good explanation as to why that is. There have been some suggestions that it could be an impact structure or a weird heterogeneity in the mantle that's some sort of process that's fueling this early on in its history. But when someone solves that, please let me know. This is crazy and awesome. You can see some of the big mountains like Olympus Mons. They stand out in relief, biggest mountain in the solar system, including the mountains on Pluto, which aren't very interesting, and everyone should forget about those. So through the history of Mars, we've had a number of really interesting things happen. You've got these very large impacts that show up early in its history, even prior to the Noachian, which is the oldest period of Martian history. The magnetic field is thought to have shut off about 4 billion years ago. That would have protected its atmosphere from erosion by the solar wind. You've got large periods of volcanism stretching through the Noachian into the Hesperian, so from about 4 billion years ago to about 3 billion years ago. And then you've got some suggestion of hydrothermal subsurface circulation or flow of water, even on the surface potentially. So you have this open system where you have potential surface waters. Whether or not those are long-lived episodes of liquid water on the surface is still an open question. And minerals are complicated. I won't get into them very much, but we will have a couple of talks about looking at terrestrial analogs for those. This is not a big image. Thank you. So another one of the talks we're going to be getting is looking at the subsurface of Mars, and so I wanted to make sure everyone was on board with what that might look like. So for example, early in the Martian history where it had a higher geothermal gradient, you can see that the temperature below the surface gets up above freezing, but there's still a suggestion that early in its history the surface was below freezing, at least in some places, which may have been the location for a paleocryosphere. So you could have potential living organisms in these salt brines close to the surface, fueled by these geothermal gradients. Nowadays, things are a lot cooler, so in order to get down to the freezing point, you have to be about 5 kilometers depth. These are still purely hypothetical geothermal gradients. We have to actually send somebody there to measure these. Go geology. And so this is a very sort of simplistic view of it, and really what you could have is these very complex systems where you get penetration of, for example, brines or even liquid CO2 could be stable in the subsurface. You could get circulation through a lot of different strata. You could get mineral, water, CO2 interactions. You could get magmatic fluids or deep hydrothermal circulation. Again, you got to send somebody to go drill. Another thing we may hear about today is the Gale Crater, eponymously, because of the fact that we put a couple of landers in here, or just the one, I guess, MSL, just one. You know, they've put so many landers on the damn thing. And it's got this suggested alluvial fan structure. So you could have liquid water flowing on the surface into this crater, which could get you some sedimentary minerals on the surface, which may be easy to see. Now, speaking of minerals, there's been some suggestion that, for example, looking at John Klein with one of the SAM instruments, or the SAM instrument, I should say, you get the presence of water, carbon dioxide, oxygen, and some forms of sulfur. What those might be, still a little nebulous, trying to work out the details. Sulfur chemistry is complex. We'll get back to that later when we talk about a different planet. And one of the talks is going to talk about alunite and jarosite. Alunite is the aluminum-bearing sulfur mineral, and jarosite is the iron-bearing one. I can't tell the difference. Hopefully someone will tell me about that today. We're going to completely switch gears. Mars is super interesting, but we have to talk about the other session, which is talking about planetary atmospheres. Going interior to the Earth, we have Venus here to scale. The orbits are not right, though, so don't take that at face value. But Venus is exceptionally warm. Again, my atmospheric compositions didn't show up, but we're going to play with it. So the day is about 6,000 hours long. And the year is about 90% of a day. So it's super slow rotating. It's in a retrograde rotation, so it's really weird. It interacts with its atmosphere in crazy ways. And it's about the same mass and radius as the Earth. It's often considered to be the Earth twin if Earth had a really hot twin. And I mean that. Thank you. And it gets a lot of radiation. It gets nearly twice as much as the Earth does. So it's a very hot place. It has a 90 bar surface atmosphere that has like 700. It's hot enough to melt lead. It's really crazy. And its atmosphere is mostly CO2, about 90 bars of the stuff. And there's a little bit of nitrogen and a little bit of argon. Essentially no water. There has been some suggestion that chlorine is pretty present in its atmosphere because you get melting of sodium chloride, which is just crazy. And so speaking of crazy, this is an example of some of the chemistry we think is happening in Venus's atmosphere. I'm not going to go through this all, but you can see that essentially we're starting with like SO2. I can't even find it. Here it is. SO2, and we're using SO2, for example, photochemistry is happening. You're getting some chlorine chemistry that's also happening, and so you get the exchange between these reservoirs, between like SO2 and pure sulfur species. You can get some sulfur aerosols, some complex sulfur species. You get like, I don't even know what that's called, but basically chlorine is a big part of a lot of the chemistry that's happening in Venus's atmosphere. Just to show you it a different way, you can do a lot of emissions. For example, these are photon emissions. I'm not going to suggest that I know what these symbols represent, but you can see that the reservoirs are exchanging constituents. So, for example, CO2 gets photolyzed into O and CO, and then those species go on to do different things. That's not at all like what's happening on the Earth. And so on the Earth, you can see here that you do get some oxygen production from the photolysis of CO2. But on the Earth, oxygen is entirely within the domain of biology, at least in the present Earth. If we look at oxygen through time, oxygen prior to the rise of oxygen at the Great Oxidation Event about 2.5 billion years ago, oxygen was very low and rose to between 1 and 50% of modern. And then there was a second rise of oxygen about 600 or 800 million years ago that it rose into about present values. If we look at oxygen on other planets, though, as an analogy for building out a photochemical framework for understanding terrestrial planets, there's been a suggestion that the incident stellar illumination as a function of wavelength can alter the photochemistry and the photochemical steady state of the terrestrial planetary atmosphere. And so these are the fluxes with respect to wavelength, and these are some of the relevant cross-sections, for example, for dissociating CO2 and oxygen and ozone absorption. So with that, I will take questions because I'm 30 seconds over time. Thank you.
Questions for Sunny?
Oh, Kai, come on. Somebody's got to want to know something about Mars. Okay,
All
question
right.
in the back.
Great talk. You said there are hypothetically hydrothermal fluids on Mars. Does anyone have any hypothesis on what the geochemistry of those fluids might be?
So the suggested liquid water layer in the Martian subsurface is fairly deep because the geothermal gradient is so weak. So it's really a question of what composition those liquid water layers are going to have. I would suggest that they're going to be, if they are liquid, they're going to be incredibly briny. So 30 or 40% salt solutions.
Like Earth, unlike Earth.
You can find some of those crazy brines in a lot of. There's a couple of really interesting salt environments where you can get those brines on the surface of the Earth. I don't know if they're great analogies for the subsurface of Mars because you also have to worry about the pressure that you're at. I didn't suggest it, but you're at like 1 million atmospheres at 5 kilometers below the Martian surface. So it's going to be pretty weird. But
Right.
Welcome to terrestrial planets.
Right, thanks.
I'm going to ask a question about Pluto just because people talk about Pluto as having an atmosphere, and part of your talk was about planetary atmospheres.
Right.
Does Pluto actually have an atmosphere? Or is it more like a surface-bound exosphere like what's on the moon? Do you have any idea?
I think that, I mean, the classical idea was that it was a surface-bound exosphere. But I think that that's still pretty commonly held. It actually, when Pluto and Charon come close enough together, Pluto and Charon share an atmosphere. It's actually the scale height rises to the point where you get actually atmospheric transfer from Pluto to Charon, which is, again, pretty crazy. That just blows my mind. But I think that it's still considered an exosphere at that point. So.
Thanks.
What's that? Yes.
All right, let's thank Sunny again.